Thanks so much for the invitation from Ori and Bernard. So, I have this chance. I would like to present our recent efforts in terms of modeling and prediction of hypersonic wall-bounded turbulent flow. So this work has been, collaborated with my student, PhD student Song Depei, Shen Jian, Yuan Jia, and my postdoc Liang Tian. Previously, also my PhD student in UST, and Dr. Zhao Zhiye and Dr. Chen Xianliang at UST. And also some of parts was collaborated with Dr. Kevin Griffin and Paris Moyne when I was postdoc at Stanford. So we all know that turbulence is a chaotic multi-scale flow phenomena. So there is a broad application from wind energy, submarine application, ship industry, atmospheric flow, and etc. And apparently, the most important application from our perspective is in aerospace engineering, especially when we concern about the CFD prediction of the aerodynamic flow. So that heavily rely on the accurate prediction of the turbulent flow. And here we show one animation from experimental measurement about the multi-scale nature of the turbulent boundary layer. You can see that, right? With the increase of the RE tau, the Reynolds number, so the boundary layer becomes thicker and thicker, and you see this coherent motion, which is multi-scale and chaotic, but also you can see some patterns appear, right? So it's rather challenging to do direct numerical simulation to resolve all the scale if we want, especially as a practical Reynolds number for aerodynamic applications. So today I'm going to tell a few stories, 6 short stories. I want to convince you that by doing fundamental research, we are able to deliver a useful prediction and modeling tool for the compressible turbulent flow over complex geometries with industry applications. So if you want to check the details, you are more than welcome to visit my website. So we list most of the work has been published in GFM, PNAS, physical real fluids, etc. You are welcome to check the detailed formula. Okay. So the first short story is about compressible law of the wall for channel pipe and boundary layer flow. So I guess this plot is elementary for all of us from textbook. If for incompressible boundary layer flow, regardless whatever Reynolds number, you can see that if you have proper normalization, for instance, with the u tau as the velocity scale and the viscous unit as a length scale, you get u plus y plus, and you plot them together. All the data together, you will see that below the logarithmic regime, you get a perfect collapse. Okay, in both viscous sublayer, buffer layer, and log regime, you get this collapse. So the different Reynolds number eventually only change the outer regime of the boundary layer. Okay, and this collapsing log law, this universal law of the wall actually build up the foundation for turbulence model of incompressible wall-bounded turbulence. Then the question is that how about the compressible law of the wall? Do we have a compressible law of the wall? So if we want to directly derive a new compressible law of the wall for hypersonic high-speed wall-bounded turbulence with different thermal conditions, different Mach number, different Reynolds number, it's rather challenging. The point is, inside the boundary layer, in compressible flow, in hypersonic flow, so all the variables are changing, like temperature, viscosity, velocity, etc. Okay, so it's really hard to derive a simple scaling. So what we want to do is that we alternatively we want to develop a so-called velocity transformation. We want to transform the compressible velocity profile into the incompressible counterpart. Because we have the incompressible law of the wall, if we also have the effective velocity transformation as a bridge, then that means equivalently to say we also have the compressible law of the wall. Okay, I repeat again, you have an incompressible law of the wall, right? And also if we have an effective velocity transformation to connect the incompressible and compressible flow, then that means that is to say we also equivalently to have the compressible law of the wall. Okay, this is the indirect proposal. So in terms of regarding the velocity transformation, we can trace back to Van der Reest in 1951, and later there is John's physical review letter paper 2012, and then we have the famous Tretter-Larsen transformation in 2016. We also have Volpiani in 2020. This is a dead-driven approach. So I briefly review some of them to give you some idea. So the one-dimensional transformation essentially assumes the incompressible mixing length L plus and the Reynolds shear stress are both Markov invariant function as a function of y plus. Okay, the length scale is y plus. And based on these two conditions, they directly derive this density-weighted non-dimensional velocity mean share as a Markov invariant function. Okay, and because this is non-dimensional mean share, so velocity this is has a dimensional, it's non-dimensional, but it has the mathematical physical meaning of velocity derivative. If I do integration from the wall to the far field, then you get the velocity scale. Okay, so we call this density-weighted transformation as a one-dimensional transformation. It actually works perfectly for adiabatic boundary layer flow as shown in the top. You can see that with different Reynolds number, so essentially they all collapse where in the log regime and below. Okay. However, if we move to flow, boundary layer flow with heat transfer, you get a strong deviation in the viscous sublayer and log regime and etc. So it's apparently not universal. Later on, we have the Jones transformation in PR paper 2012. They assume that Reynolds shear stress tau R plus and the turbulent, this ratio, which is essentially turbulence dissipation divided by the non-dimensional viscosity, this combined term, they are Markov invariant function as y plus. So length scale is still y plus. And this is the two conditions, and they further assume that the turbulent production and dissipation are in near balance. Okay, they get production term equals dissipation term. So with all this condition together, the derived so-called Markov invariant function of this new non-dimensional mean share, which you can see that is not density weighted, instead is viscosity weighted non-dimensional mean share. They also do integration from the wall to the far field. You get the transformed velocity scale. We call it a Jones transformation UZ. And actually, it also works well in adiabatic boundary layer. But for boundary layer with heat transfer, you get a strong deviation in the logarithmic regime. Later on, we come to the Tretter-Larsen transformation. This is a very famous transformation proposed in 2016, if I remember correctly. The first assumption is a constant stress layer in the near regime. Secondly, very importantly, compared with the previous Wanderist and Jones transformation, is that they introduce a semi-local scaling. Okay, the length scale now changed to y star. And the velocity scale, they propose this semi-local viscosity-based non-dimensional Markov invariant non-dimensional mean share. Okay, after integration with regard to this semi-local y star semi-local coordinate, then they get a Tretter-Larsen transformation. This Tretter-Larsen transformation, I would say the derivation is not rigorous. However, by chance, it works perfectly for channel flow. Okay. What I mean is not rigorous because the constant stress layer in the log regime essentially is not valid. Okay, so only in the very near wall regime you probably can retain constant stress layer. We all know that in channel you have a linear distribution of the total shear stress. And this Tretter-Larsen transformation, it works for channel perfect, but for boundary layer with heat transfer, you still get a strong deviation. However, when we re-examine the all the derivation, figure out that the assumption in the near wall regime, in the viscous sublayer, it should work perfectly as expected. So now it comes to the story that we examine all the transformation. None of them work for all the flow, channel, pipe, boundary layer with and without heat transfer. None of them works. Now the single scaling works for all the flow. So the idea is that for a viscous sublayer in this regime and the log regime, essentially there are different physics, right? One is dominated by mean share, the other is dominated by Reynolds stress. Different stress, different physics. Why we insist on one scaling? Okay, so and also which means that equivalent to say we can have different scaling in different regime, right? To respect the different physics. And also we figure out, as we just mentioned, Tretter-Larsen transformation is not working in the log regime for all the flow, but in the viscous sublayer it works perfectly. So the idea is that can we propose a new velocity transformation for log regime, and then we composite them together. Okay. So in the Pinas's paper, we propose this equilibrium transformation for diabatic flow. Okay, we assume Reynolds shear stress and this epsilon star are Mach invariant function, by the way, is a function of y star, also semi-local scaling. And we also introduce the turbulence production dissipation assumption. They are in near balance, so their ratio is a Mach invariant function of y star. So we get F3. We do not assume production dissipation are equal, but we assume their ratio is a Mach invariant function as y star. Then we derive this new Mach invariant function. This is also viscosity weighted, non-dimensional mean share, but the length scale is y star. And you can see that for channel pipe flow as above, and for the boundary layer flow as below. And you can see below figure. So in the logarithmic regime, this pink line, from our new transformation, we get a perfect collapse to the incompressible counterpart, which means that at least for this new transformation, it works perfectly for the logarithmic regime. The idea then comes, we propose a total shear stress based transformation. People later on also call it the GFM velocity transformation. Okay, during this new transformation, you can say it's a composite or hybrid transformation. So if you analyze this transformation, you figure out that in the near regime, the mean share will dominate the total shear stress, and the transformation will recover the Tretelazzo transformation, which we thought the derivation is reasonable in near regime. But if you go to log regime, you figure out the transformation will recover the near balance of production and dissipation. We get our Pinus equilibrium based transformation. Okay, so it's essentially a composite transformation in different scaling, different regime. And we select 49 cases, 21 from supersonic channel pipe flow, 15 from adiabatic flow, 13 from diabatic boundary layer, and the Mach number 0 to 14, Reynolds number from 200 to 6,000. Okay, then I just for short I put all the data together to examine the performance of different scaling. Like John's transformation apparently does not work for the log regime. Tretelazzo transformation also deviate a lot in the logarithmic regime if it is not a channel. Our new transformation, we call it total shear stress or GFM transformation. We get a perfect collapse, for all the different database collapse to one single line, which means that we get a perfect compressible load wall. Then the question for the next short story is about, we have a velocity compressible load wall. Can we have a temperature load wall? I mean, this is a really explored in the history. Okay. So if we want to get a load wall for the temperature, it's more challenging. So if you check the energy equation, temperature appear in the energy equation mainly, right? This is two-dimensional energy equation, right? So apparently, according to boundary layer assumption, some small magnitude term can be neglected, right? So the first, the second, and third term can be removed. Or balanced each other. So left term is can be simplified in this one normal derivative. And if we do the integration in the y coordinate, you get this balance law, for heat flux. And if you consider this enthalpy definition H, you can further expand H enthalpy intermol temperature. Then you get more fluctuation term. And this triple correlation can be neglected. Apparently, it's a small magnitude compared with other this prime u prime v prime this double prime term. So after you remove this term, you can further incorporate the so-called constant stress layer assumption if you consider very near one regime, and then you get a simplified governing equation for the energy. This is looks like first of all you have temperature, and secondly it's rather simple. Okay, then people start to propose so-called semi-local type temperature transformation. There are not many work in this regime, but let's revisit a little bit. Okay, so they first introduced a turbulent eddy viscosity alpha t, which is classical definition. They also introduced a semi-local friction Reynolds number. Then they define theta equals t minus t wall. Then they get the governing equation previously we derived can be simplified in this version. Okay, you get three terms: psi 1, psi 2, and psi 3. Based on the low Mach number DS dataset, Patel in 2017 demonstrated that for given Planck number, so psi 2 this psi 2 this combined term can be a Mach invariant function with respect to y star. Okay, And later on, further address the aerodynamic heating effect. So Chen, this paper, they further assume that psi 2 and psi 3, their ratio is a Mach invariant function. And later on, we call it the semi-local scaling. Okay, they get this scaling, and this scaling, this Mach invariant function phi SL is Mach invariant function with regard to y star. So it's a semi-local coordinate. Okay, we call it a semi-local type transformation, which works reasonably well for channel flow, but not for boundary layer. Not for boundary layer. Okay. There is another type of one-to-rest temperature transformation. Okay, this is essentially similar to the velocity transformation. So by analogy with the invariant function governing the mean velocity transformation in compressible wall turbulence as originally proposed by one-to-rest. So we can also propose a density-weighted, one-to-rest type of temperature transformation. This is the original format. And me with my student, we also propose this improved one-to-rest type Mach invariant function and scaling. So you can see that density-weighted function still remain, but we change the length scale from y plus to y star to better account for the compressibility effect. But all of this transformation, one-to-rest and previous semi-local type, they are not working perfectly for boundary layer. Boundary layer flow is very difficult because you have different thermal condition, different Mach number, different Reynolds number, so it's much more complicated than channel flow. So what I thought, the idea is that similar to the velocity transformation, you different regime have different scaling. In temperature, you can also have different scaling for different regime, right? We first propose improved semi-local type transformation for viscous sublayer. We first get a perfect scaling for viscous sublayer. Then when we examine the previous state-of-art semi-local type transformation, we figure out that they utilize the local heat flux as a reference scale for the mean heat flux. But we figure out that if we replace the local heat flux with the total heat flux, you can see that from the blue line to red line, you get a better collapse to the incompressible line, incompressible data, which means that this length scale, total heat flux length scale, is more rational as the reference length scale. And however, this involves the fluctuation term, right? Turbulent heat flux, which is not it will prevent this model as turbulence eventual range model if you involve this fluctuation term. So we, in order to avoid this turbulent heat flux, we propose a turbulent heat flux model based on the this mean velocity distribution. Okay, this is totally based on mean velocity distribution. We get this turbulent heat flux model, which, as you can see here, this red line in the neo regime, viscous sublayer, it agrees with the DNS turbulent heat flux very well. Okay, then at this point we reach the so-called improved semi-local type transformation for viscous sublayer. Compared with the previous version, we have additional term in the denominator. Okay. Then we check our performance in the viscous sublayer. We show different Mach number, from 2, 6, 8, and 14 different type of thermal condition. And you can see that the state-of-art semi-local transformation and this one-to-rest type of transformation fails, apparently not perfect in the viscous sublayer. But with our new transformation, improved semi-local type of transformation, we get significantly better collapse in the viscous sublayer to the incompressible database. And also in the log regime, we also propose a new one-to-rest type of transformation. Okay, we return this density-weighted terms, which is motivated by one-to-rest. But we also add one density-weighted term in the y-coordinate term. Okay, then we reach a so-called new one-to-rest type of transformation for the low log regime. And you can see that compared with state-of-art semi-local and one-to-rest type of transformation, we also get a significantly better collapse in the logarithmic regime. Then the idea comes, follow the GFM transformation as we just mentioned, right? We just composite the two transformation, improve the semi-local type transformation in the viscous sublayer and the one-to-rest type, improved one-to-rest type of transformation in the logarithmic regime. We get a new composite transformation for temperature. And let's examine the turbulent boundary layer with adiabatic and heated wall. You can see that the classical, semi-local, and the state-of-art one-to type transformation, they all fail to collapse the database or compressible flow to the incompressible limit. However, with our transformation, you get perfect collapse. If you consider more challenges, supersonic turbulent boundary layer with cold wall, supersonic flow, Mach number up to 5, you can see we also significantly improve the previous two state-of-art transformations. And if we consider the most challenging, like hypersonic turbulent boundary layer flow with cold wall, so the classical transformation, semi-local and state-of-art boundaries, they all fail significantly, substantially, and we get a perfect collapse, which means that we succeed to derive a new temperature load wall for compressible boundary layer flow. Okay, so now we come to the third story. Okay, we have a compressible load wall for the velocity. We have a compressible load wall for temperature. How about the velocity temperature relationship? Okay, this is for high-speed turbulent boundary layer flow. The relationship between temperature and mean temperature and velocity are central problem actually. Can be traced back to the test book Kirk-Bussmann in 1930s and Wars 1970s. Okay, the important contribution comes from the milestone work comes from Duan Martin in 2011. So they propose this quadratic relationship. However, this constant CT is from dead fitting. Okay, and later on we have a more theoretical interpretation from Zhang in the physical review in the GFM paper that propose a generalized Reno analogy. Okay, it is still a second order quadratic function between velocity and temperature, but all the parameters can be interpreted by this Planck number and Reno analogy factor, etc. It's not from dead fitting. Okay, how the interesting stuff is that this derivation eventually result in this relationship, which is identical to this fitted correlation, which is interesting. And now this VT relationship was validated to be highly accurate for turbulent boundary layer channel pipe for both adiabatic and diabatic flow, which is amazing, right? Why it works. And people also figure out that this quadratic relationship somehow also, if you choose a proper RG recovery factor, it also works for laminar boundary layer, okay, which is also surprising to me. Then with my student, we try to, get a motivation for our work. We want to understand why this quadratic relationship will work for different flow. What's the assumption? When the assumption will be valid and invalid, and if the relationship works, why it works. If it does not work, how to improve. We want to fundamentally analyze this relationship. So we start from this this analogy. Okay, this we call it a Reno analogy, right? The left is enthalpy, right is velocity. So if the Planck number is 1, then the total the enthalpy and the velocity has a perfect relationship. However, typically because the Planck number is not 1, then they introduce the recovery factor Rg to define the new total enthalpy. They call it Hg. Hg is not in the kinetic energy term there is a Rg prefactor. Okay, it's different from the classical total enthalpy definition. So this relationship there is unknown parameter Rg. Okay, if you expand this enthalpy in terms of variable temperature, you get this second relationship. Later on, they do further derivation. Okay, they define this general recovery factor Rg and also effective Planck number in this formula. Then they combining with this original relationship, they form a ODE. They call it a TV relationship ODE. Okay, so this ODE is very interesting. This PRE, if you have assumption PRE equals 1 and Rg equals constant, this ODE will have analytical solution. That is exactly the quadratic relationship as we shown before. And the boundary condition here, partial T, partial U at wall simply can be closed by introducing the Reno analogy factor, which is supposed to be a constant in hypersonic flow. Actually, this is also empirical constant. However, it's very validated. So So the point is, we want to know for different type of flow whether this assumption is correct and why the relationship works. So first, we examine the this so-called TV relationship for laminar channel flow. You can see you get a perfect collapse to the DS TV relationship. But if you examine the assumption RG is not constant apparently, okay? But PRE equals 1 is very robust. It's very robust. There is a deviation, but a deviation in the outlier regime. Okay, in order to explain this deviation will not affect the accuracy of the relationship, we introduce a novel tool that is a sensitivity analysis. We figure out that even though there is the deviation PRE in the outer regime, the sensitivity on the solution is very low, and eventually does not affect the prediction accuracy. Okay, you get so this relationship works for laminar flow perfectly. So later on, we examine the this relationship, TV relationship for laminar boundary layer. And RG is not constant. Again, this assumption is not valid. But PRE, although it's not 1, but you have a perfect collapse to a single line, which means that if PRE is not 1, then we cannot have analytical solution to the VT relationship OD. We cannot have exact analytical solution. However, we can have numerical solution. We can parameterize this PRE, it's not the 1, but we can parameterize this trend, and then we can improve the numerical solution as a model. Okay, eventually we can decrease the prediction error significantly. Okay, for turbulent boundary layer and channel, we select 7 DS data set for turbulent boundary layer and 12 for turbulent channel to verify the solution and the relationship. And we figure out that, as we know, that as we already indicated that for turbulent boundary layer, the VT relationship works perfectly. Okay, but if you really examine assumption RG is not constant, by the way. But PRE for this adiabatic and heated wall, you can see that PRE is almost a unity is 1. But for the cold wall, you can see there is a strong deviation. Indeed, there is a singularity problem here in the definition, PRE definition. So there is 0 by 0 issue in the neo regime. So we get this strong deviation from unity. So, however, we also did the sensitivity analysis, which is very strong in terms of mathematical background. Eventually, we figure out that although there is a strong deviation in the neo regime about the PRE equals 1 assumption, however, sensitivity on the solution is very low. That explains why, although the assumption deviated from the ideal condition a little bit, but still you get perfect prediction quality. For the turbulent channel flow, again, RG is not constant. This assumption is not important, actually, as you can see here. It's never valid. But PRE equals 1, it also moderately differs from 1, but there is a pattern. If there is a pattern, we can parameterize the PRE. Okay, we can get a numerical solution. We can reduce the prediction of the TV relationship compared with DS from error to 2.4% to 1.1%. Okay, so which means we get some conclusion. For laminar flow, this TV relationship is highly accurate. For laminar boundary layer flow, it systematically deviates. However, we can improve the prediction by a new PRE expression parameterization. For turbulent boundary layer, it's highly accurate. For turbulent channel flow, it's moderately deviates, but we can also improve by fitting a new PRE expression. We also get another conclusion is that the RG equals constant. This assumption in the entire derivation is not important, okay, at least from a posterior analysis. But the PRE equals 1, this is critical because this determines the quadratic relationship, okay. PRE equals 1, this assumption is very important, okay. So we have now we come to the fourth story. We have a compressible load wall for temperature, for velocity, and we also understand the velocity temperature. There is a quadratic relationship. So how can that help us to get something more interesting conclusion? So then we reach the story about the general skin friction scaling law for compressible turbulent boundary layer flow over flat plate. This is actually a textbook problem, okay? If you go back to check the textbook for turbulent boundary layer flow, you know that CF and RE theta, this moment thickness Reynolds number, actually there is a long relationship. This was like validated by many numerical DNA simulation result and also the experimental data, okay? So it's from Najib, from many historical paper, so you can get this relationship, okay? But if you think about that, that's for incompressible flow. Again, if I want to extend to hypersonic or bounded turbulence, so the CF is not only just a function of RE theta, it's also a function of Mach number, which indicates the compressibility, and also a function of this wall temperature effect, that is a heat transfer effect, right? So then how could I get a unified scaling law for skin friction? Okay, so the main idea actually is similar again. So from beginning to the end, I have a systematic idea to derive the new scaling. So the idea is very similar to the velocity transformation. So if we can figure out expression FC and F theta that can transform CF and RE theta to the incompressible counterpart, then we can unify all the the skin friction scaling law similarly to the temperature and velocity scaling law, right? As long as we have this FC, this is CF and RE theta is compressible version. If we have this F prefactor FC and F theta as a transformation parameter, then we can transform them back to the incompressible counterpart. Then we get a universal law relationship here for all kinds of boundary layer flow from incompressible to hypersonic. So if you check the textbook again, you will have figure out one Drist. One Drist is really genius in terms of modeling hypersonic or boundary turbulence. So the one Drist two transformation is given here, and we also have chi spotting transformation, which is a little bit later. So if you check the recent publication, even from this is Duan's paper, Lin Duan's paper from Ohio State in 2022, you can see that the transformed CF and RE theta apparently is not working, right? It's not working. They are not collapsing to the incompressible skin friction law. So apparently there is a strong deviation, substantial deviation. Okay, then how could we do that? How could we get analytical transformation to get a universal scaling law for skin friction? So let's check the RE theta definition. Okay, this theta essentially is a moment thickness. Apparently, this thickness is strongly affected by the velocity. Okay, and the velocity was strongly affected by the heat transfer and the compressibility. So if we want to derive FC and F theta as a final transformation, we first need to observe the compressibility and heat transfer effect. So what we do is that we redefine the Reynolds number, RE theta star, you can see here. So the velocity now is not the original velocity, actually, it's a transformed velocity with our Peanuts paper GFM transformation or total shear stress transformation. With this redefined velocity, actually, it will be independent of Mach number heat transfer effect. Okay, so this is the key idea. Okay, we redefine the velocity as the transformed velocity that can eliminate the Mach number and the heat transfer effect and collapse to the incompressible Reynolds number. And then we introduce a log law assumption to analyze this new RE theta definition. During the entire derivation, we use asymptotic method. We only return the first order asymptotics and neglect the high order terms. And eventually we can get analytical expression for F theta star and FC star as a prefactor transformation prefactor of CF and RE theta. And that can effectively transform it to the incompressible CF and incompressible RE theta. And with this new transformation, we will collapse to this law distribution. Okay. So that's the idea. So then we check, broad database from Mach number 0.5 to 14, RE top from 100 to 2,400. So our null transformation indicates that our data correlation is 0.99. By the way, this is not that fitting. This relationship now is purely derived by asymptotics. Okay, this formulation is theoretically derived. Okay, only neglect high order terms. And if you check the one Drist and G spotting, the data correlation is 0.85 and 0.86. We apparently get better agreement. If you check the absolute error prediction for skin friction, you can see that okay, our error prediction is within 5%. The classical version is can be up to 15%, which is rather large compared with an uneven application. You can also plot the CF versus RE theta in this long relationship, right, directly. So you can see that all the data from our new transformation that collapse to the incompressible skin friction law pretty well. But for the classical transformation, you get a strong deviation, Okay. Now we have lots of scaling law, right? We have temperature scaling law, we have for compressible law of the wall, we have velocity compressible law of the wall, we have velocity temperature relationship. Now we also derive the skin friction scaling law for the compressible boundary layer. So what can we do with that? What can we do? Why it is useful for us? We actually can directly predict the mean profile for compressible boundary layer without solving the governing equation. We can get a direct prediction. This is the motivation, okay? If we are, let's say from an experiment, okay? If you are given the basic measured information like Mach number, Reynolds number, boundary layer thickness, and wall thermal condition, wall temperature, can we direct, because for in experiment, mostly you cannot directly measure all the quantity like density, velocity, temperature in high accuracy. I guess it's very, very challenging for hypersonic boundary layer flow. So can we directly get this mean quantity, okay, without solving the governing equation, just based on the scaling law, okay? The answer is yes, okay? We check the available scaling law. For the incompressible boundary layer profile, we can have this colors profile we will show you later. And we also can connect the incompressible velocity profile to compressible velocity profile by the velocity transformation, for instance, our GFM transformation. We also can get the temperature from the velocity temperature relationship. We just indicated that. And we also even have the skin friction scaling law for all different Mach number flow that can give you another condition to close the system. Okay, so a story like this. First, we can if you give me RE tau and boundary layer thickness, I can uniquely define the incompressible boundary layer profile by composite the inner regime, inner log law plus a vec law, right? Inner log law can be, it's essentially just a log law plus a damping function. It's very classical, right? For the vec regime, we can use a vec component. This is a sine function. This is from the Coller's paper in 1956. And the only unknown parameter is pi, because pi is related to the Reynolds number, okay? And this, as long as you have the velocity profile of incompressible flow, you can actually map it to the compressible boundary layer profile by velocity transformation, okay? So essentially in the regime, for the inner velocity profile, we can reversely transform the velocity profile from incompressible counterpart to the compressible velocity profile by GFM transformation. And for the outer regime, you can use the one derivative transformation. Okay, now you have a incompressible velocity profile. You also have a bridge that is the GFM and VD transformation that can transform the incompressible counterpart to the compressible velocity profile. As long as you have the velocity profile, you can also utilize the quadratic relationship or temperature velocity relationship to predict the temperature. And you have temperature, then you have viscosity, and then you have all the other variables. You have density, and etc. Okay, but there is unknown parameter at the beginning, as we mentioned. In the incompressible velocity profile, there is a sort of the pi. This pi parameter in the vector regime is undetermined, right? So how to determine this? If you need actually additional condition to determine this pi to close this system, okay? Because you have an incompressible velocity profile, you have a transformation to map the velocity profile to the compressible version, and you have a temperature profile that can be obtained from the predicted from the velocity profile. Then the only unknown parameter in this system is the pi, okay, in the incompressible definition. This pi can be determined by enforcing the scaling law for skin friction coefficient, as we just derived, okay. This skin friction coefficient can be applied to any Mach number from 0 to Mach number 14. So it's a long distribution. That's additional constraint, okay. Then we can form this loop to solve iteratively. Very simple, actually. It's just it's an ODE solver. Simply solve ODE solver, we can determine the vec scaling factor pi, and then all the parameter, all the velocity, incompressible velocity, compressible version, and compressible temperature, viscosity, density, and can all be determined, okay. So we can do a prior test. Prior test means that the mean temperature is obtained from DNS data set, not from VT relationship, and we only concern about the velocity prediction. You can see that the present framework we actually have, can restrict everything to be the error to be like a 6%, which is significantly lower than Hesson and Larsen's method to predict the mean profile. If we do posterior analysis, okay, this is for adiabatic boundary layer from Mach number from 0.5 to 8. Reynolds number I talk up to 1000. You can see that we get perfect agreement for both velocity and temperature distribution. Okay, and this is for diabatic boundary layer with heat transfer. Again, Mach number up to 8. Reynolds number up to 2000 RE-tau, and wall condition can be very cold to even hot heat, and you can see that we still get a very good agreement for both velocity and temperature prediction. In terms of the prediction error, velocity, temperature, skin friction, and CH, we can restrict the error to be like less than 5%. And you compare with other method published paper recently, so we get the minimal error prediction, okay? Especially with our own GFM transformation for velocity, we get a 4% error for both temperature and velocity in terms of the mean profile. Okay, which means that now if you want to simulate a hypersonic boundary layer, if it's boundary layer, you don't really need to solve the Navier-Stokes equation, Rand's equation, and also you don't really need to do experiment to measure everything. You only need to give me the Mach number, Reynolds number, and the boundary layer thickness, etc., wall thermal condition, and then we will directly give you the mean profile. And that will be very helpful for experimentalists, I'm pretty sure. So we have so many scaling laws. Then how to really, just now we mentioned that we can predict flat plate directly, right? You don't need to solve the governing equation. But how about industry application, right? With complex geometry. So we can incorporate all the scaling law into a warm boundary layers framework, okay? It's a new warm layers framework to predict industrial applications. For instance, let's consider the LES governing equation, which is, everyone notices this, right, from textbook. And you will, after filtering, you have this subgrid stress term and heat flux term. And you have two ways. One is explicit method to close this system, but also you can have a numerical method as implicit method. I would prefer my Tino scheme to close this, use the numerical dissipation term of the Tino scheme to close this subgrid scale term. So classically for warm areas from Larsen's work, actually for the compressible flow that mostly solve this ODE model, but this ODE model apparently is not accurate for hypersonic flow. You can easily do the prior test. As long as the Mach number is high, compressibility is high, thermal heat transfer is high, so the error is unpredictable. It's can be very high, or can be 100%. So what we do is that we do not solve that OD model, okay? For the velocity modeling, we directly solve the so-called GFM velocity transformation reversibly, in a reversed manner, okay? Which means that because the transformation, the original idea is to transform compressible velocity profile to the incompressible counterpart, but of course you can do the reverse mapping, right? If you do reverse mapping, you can map the incompressible mean profile to the compressible velocity. Okay, this is the modeling velocity. For temperature, as we mentioned, we have the newly derived VT relationship. It's a quadratic relationship, and also we have published GFM paper to eliminate the dependence on the edge value. So it's really useful and deployable like VT relationship, very easy to implement, and it's even algebraic. You don't need to solve OD. Okay, it's even easier in terms of implementation compared with this classical OD model for the energy equation. In order to handle complex geometry, we utilize the block structure Cartesian grid, okay? And we further introduce the Cartesian method. Your Cartesian method can easily handle, arbitrary complex geometry. That's apparent. So in terms of numerical discretization, we utilize hybrid Tino-Kip scheme. We introduce Kip scheme in order to, it's all 6 order. The Kip scheme is it's a little bit cheaper than Tino scheme, right? But the Kip scheme cannot handle shock value, and compressibility. So the Tino scheme will handle this highly compressible regime, and the Kip scheme will handle the linear regime mostly, and we get 6 order accuracy. And also this Tino dissipation can function as an implicit LES model to replace the explicit model, which is actually not necessary in compressible flow. It's actually, if you add that explicit model, it will be over dissipative. So in the near world regime, we introduce cut cell method to handle arbitrary geometry, and in the apparently here you cannot use a very high order, so we introduce this second order hybrid slow keep scheme in the very near world regime. You cannot deploy Tino because there's not enough stencil. Okay, because this cut cell method, so this near world turbulence cannot be resolved where, so we deploy the model, the new model, right? Inverse velocity transformation and also VT relationship. We deploy that model, reduce the other model between the wall surface and to the third matching point, okay, in the near world regime. So you like the entire domain is discretized with LES scheme and solution, and then you extract the data from this matching point, and then in the one normal direction you deploy this near wall transformation and the VT relationship to get the wall shear stress and heat flux to close the entire area system. That's the typical implementation of the one model LES. Okay. I think time is almost over, so let me quickly wrap it up. So we do accuracy test. We can achieve like a fifth order. But eventually you will convert it to fourth order if you have non-uniform mesh, because across the resolution we deploy the fourth order interpolation. So that constrains the overall order. But if there is uniform mesh, you can reach sixth order. Okay. Here we show this shock cylinder and shock wedge interaction. We compare with the experiment. We show you the capability of shock capturing of Tino scheme and also numerical stability as well as adaptive mesh capability. And we first validate turbulent channel flow, which is a model Mach number 1.5. You can see that with our new model, for the result part, this red color and the blue color in modeled part, you can see we get excellent agreement with the velocity, and even for the renal shear stress, you can see that we still get good agreement before, above the matching point. Below the matching point, there is a 1 and 2 grid point that is numerical garbage you can actually essentially neglect. Okay, we care about the matching point above, which is the result. For the high Mach number 3 with a high Reynolds number, we compare our new model, GFM model, with the OD, classical OD model in Larson's paper. You can see that we get, apparently here there will be heat transfer. We get all the one improvement in terms of velocity and temperature prediction, right? We get excellent agreement with DNS and significantly improve the solution of the classical OD model. For supersonic flow over compression ramp, you can see again, this is a turbulent structure capture. There is a transition process because of blowing suction at the beginning. So we can capture the shock wave, and as well as the suppression bubble and etc. And then we compare with the DNS. Again, our model get a significantly improved prediction in terms of the velocity, pressure distribution, even the CF prediction. Okay. For the more complex high lift airfoil 30P 30N, which is actually a low speed flow, our model can also function because our model can typically handle the flow from Mach number incompressible flow to hypersonics, right? So typically it can also be deployed to the low speed. This is the vertical structure, turbulent structure we captured. And this is a quantitative comparison of pressure distribution, even the CF distribution. You can see here, we get a skin friction distribution. We get a very good agreement compared with the experiment. And for the wall normal velocity at different streamwise station, we compare with the experiment and other WMLES result. We again get a better agreement. Okay, this is more critical. The entire velocity profile in the wall normal direction at a different station can be well captured. This is a helicopter rotor in the Hoover state, okay, which is challenging, this adaptive mesh and the numerical mesh and etc. And this is the turbulent structure we captured, and you can see that the Tino scheme and the KIP scheme is very low dissipative. We capture all this kind of fine multi-scale turbulent structure, and we compare the tip vortex trajectory with the experiment, and again we get excellent agreement, which is indicated by this red symbol, okay, triangle. At the last, we show the NASA common research model, which is high resonance number, but also low speed. Here, we show the mesh adaptation, and this is we almost use 100 million cells, of course. This is resonance number very high. This is the animation we eventually generated. Okay, so you can see the tip vortex and this flow separation and all this kind of small scale structure are well captured by our wall model LES framework. If you have a very dissipative scheme or turbulence model, you are going to damp dampen most of the structure. And we compare with the pressure distribution with other solver and actually I didn't show that. We also compare with other experiment with that we get a very good agreement. Okay. So without further generating more slides and time, so I'm going to close my session. Thank you.